Hello, my name is Anthony Shivkumar, and in this video, this is going to be part 2 of the ARM custom development series. And in this video, I'm going to continue on where I left off in the previous video. Please, if you want to check out more about that, it'll be in the below description, the link to the previous video, and also on the top left, right. I'm just going to recap as to why we are developing a custom environment for us to, create projects for the ARM processor. And it doesn't matter whether it's ARM or AVR, but it's more about having your own environment and custom environment, no matter for your embedded needs. One of the reasons why I want to set up my own custom environment is to have my structure based on being independent of the target. What do I mean by that? You don't want your repository to change based on if I'm, just programming for the Microchip or for the NXP. You don't want your folder to just be for that particular target. You want to have a general repository, and in there you want to have a part of that a folder in that particular repository, a subfolder that caters to a specific target. So you don't want to keep changing based on on the processor or on the target. So you want to have an environment that's independent of that at least. Another reason why you want to have a custom development environment is especially when you're doing automation of the build process and testing your code. Using the manufacturer's ID is not well suited for doing these kind of things where you want to put them in the cloud infrastructure, do the build process of testing, doing your test coverages, making sure everything is fine before it's deployed onto the production hardware. You want to have an environment to allow you to do this. This is another reason why having the custom development environment can help you do this. Another reason is for easier to collaborate and share with your team members or with the open source community, depending on the direction you're going. You can't expect them to download this particular MCU Expresso ID or Microchip ID or Atmel Studio or whatever be it, or Nordic Semi, and then ask them to download that particular piece of software if they want to work with you. That's a big bottleneck to ask for anybody. You're better off creating an environment that works irrespective of the environment you want, and depending on how they want to use the code, whether they want to bring it into their IDE of choice and work with it. That's the preference. But you don't want your folder structure and the way you're designing a repository to be the bottleneck to allow more people to collaborate with your work. And last but not least, it's just better maintenance, better portability, better organization of your code. It allows you to refactor your code based on your needs, based on the algorithms, and based on the style. It allows to constantly maintain and update your code in a much more easier manner rather than relying on the manufacturer's ID, which sometimes can be, there's a lot of control given to someone else. Whereas in this case, you have majority of the control of how you want your code to be organized. And this is in a nutshell why I'm creating this small little video to really show you why you want to have that custom environment. From where we left off, I just want to give a more visual representation of our folder structure to better understand how I would create my own custom development environment. On the top, we have our root directory over here. And in the root directory is the root folder. And under the root directory, you can have, say 2 directories, which is for your source and for your include. And the include could have, some common header files that are, universal, that are common to every other subfolder. And I'll talk about it. And your source directory will have your actual C code. And then you want to have a makefile right in your root directory that allows you to build your code based on, by compiling your code and giving it instructions to how to compile your code based on all the directories that you have. And then the second part, or the second subdirectory, and then the hierarchy of how you want to organize your code. Under your source directory, you would then have things like, control systems and computer vision, because this is for a drone project. This is the way I've maintained my code, and this is how I've organized my folder structure. In your case, it might be different. But in this particular case, I'm putting on all the things that's where you want to spend most of your effort on, basically. Designing the control system algorithms and all that code would be in there, like the PID controller, lag compensator, optimal control theorem, or model predictive control, depending on what works well based on certain situations and certain parts of your robotic application. This would be, say, computer vision, things like optical character recognition, things like edge detection, or any specific computer vision, or just doing basic arithmetic with of images. Taking your image from the camera and just converting into RGB scale or converting into black and white, and then feeding that into, say, the artificial intelligence neural network algorithm. So it could do a little bit of pre-processing of the images, of image stitching and stuff like that. So those kind of things would be in your computer vision directory. Flight dynamics is all about how to make your drone fly in an efficient manner. Control system and flight dynamics might go in hand in this particular case, but this could also mean navigation and path finding and doing all the other cool stuff. And then we have a directory for hardware. And your hardware would be, the peripheral devices that you would have to have on board, like IMU sensors, ADC converter, maybe an infrared sensor or a sonar sensor. So that would be a hardware specific folder just for specific peripheral devices that you're incorporating into your system or into your application. You would have a folder for motor control, how to control your brushless DC motor or your stepper motor or your servo motor or a gimbal motor, depending on what kind of features your drone might have or your robot might have. You would have sensor fusion algorithms like, Kalman filtering, complementary filter, and, taking all the readings from your sensors, which might be in the hardware folder, and, and computing them to make sense of it. And then we have the real-time operating system folder, which could, be like FreeRTOS and all the cool, and all the others, the operating system of choice, that could be even embedded Linux. And once you have this folder, then we go to the target, which is exactly what this video is all about. As I, progress and show you how I'm progressing through, each part of the drone that I'm building, I'll be basically switching, the folder directory from target to sensor fusion to motor controller to show you how I'm, utilizing this particular way of working, especially in the software side of things. So in my target, I have basically now have a subdirectory based on the manufacturers of the target. This could be a Microchip, or it could be an NXP, it could be Nordic Semi, it could be NVIDIA, it could be Texas Instruments, it could be Intel, the Movie-Bus processor that they have for image processing. It seems to be a little promising, and all the other manufacturers. That's where you want to have their basic subdirectory. I would rather organize it based on the manufacturer, and then from there organize it based on the MCU, which is or the microcontroller unit or the microprocessor unit, and then from there organize it based on the BSP, which is both support packages. So this would be very specific to that particular embedded development board that your manufacturer might give, that will allow you to get started with the board. And that's how I would organize my folder structure. This is not the way, if you download an IDE from your manufacturer, then they won't allow you to organize your code in this way. And that's what I mean by flexibility and having your own custom development environment. And then when you click make, say make for embedded systems, so in your make, you could have certain rules and ways of, developing your board. And you can say, make for flight controller, build my algorithm for flight controller, and then your make file, would go and say, okay, we need to build the control systems library, we might need to build the flight dynamics, the motor controller, sensor fusion, and then we might need to build the FreeRTOS, then we go to NXP, then we want to go to the MCU and build everything for this particular target. So at the root directory, you're giving it instructions based on what parts of the drone or your robot you're building. Go build those particular files and then, compile it. That's really how I want it to be done. And in the same folder structure might do all my AI and computer vision, which might be a completely different processor. This folder structure will also allow me to have multiple processors to work with, which I can't do in a manufacturing environment where I can only focus on one specific processor. So I could have NXP for doing all my flight controller dynamics, and I might probably, use NVIDIA for all my AI and machine learning and doing all the neural networks and all the cool stuff. We also would want to have like an AI repository over here, which I don't have. That would change, the flight dynamics into, say, AI in this particular case, and do all the deep neural network and all the cool stuff, related to machine learning and artificial intelligence. That's how I would organize my code. And in a nutshell, I think this is a much better way to, keep your code in a way that is a lot more scalable and a lot more usable. Now let's get back to my folder structure and show you what I just showed you in the graphical format into how I've organized the code over here, which I also did talk about, in my previous video. So in here, I basically have my make file, and I have my, and my source file, source directory, and under my source directory, I have computer vision, flight controller, hardware, and in here I have my target. And under target, I have my Nordic Semi and NXP. And then since we were just focusing on this particular case, NXPs, and building our environment just for NXP, and I've got downloaded all the, these are all the processes that I'm currently working with. So currently, in this particular example, I'm using the LPC1769, and in here, we have all the board support packages. Now, all that is pretty cool. Now, how do we compile it? Because generally, if you want to compile this code, the manufacturer gives you all the tools for you to compile it using their environment. Whereas in this case, we're trying to make a custom build for this. So in my previous video, what I showed you is, how do we build, the core application and the board part. Now, to really make sense of how you want to build this, I have the manufacturer ID installed into my Linux system over here. And every time you build using their ID, this is very important. You need to download their ID. The ID is Integrated Development Environment, in order for you to understand how to make a custom build, because they're generating files and they're using certain linkers and what do you say, object files that are linked, that are generated based on some of their settings. Or when you download it, they have those files in some of the directories that you would have to link, and without that you won't be able to compile. And what do those files generally contain? And I'll talk a little bit about it, so that this is really the extension of what I did in the previous video. So, for example, if we go over here and I'm clicking, say, what do you say? So let's go to so this is the chip folder and the board NXP. So I have downloaded the environment, I've downloaded the board support packages, and I built their thing. And when you build, it'll tell you. So for example, if I go and click, say, build Blinky, it'll generate these. It'll do the build process, and the build process will give you information as to how it's doing certain things. And that information is important because you're going to take that information and customize it to your environment. So just to continue what we did from the previous video, in here I basically downloaded the environment of the manufacturer, imported all the board support packages, and I've compiled it. And it's very important for you to do this step, because you need to figure out what the build process of how the build process is actually done, because we're going to take we're going to take the way they build and what files they're linking against for us to basically do this in our custom environment. So as you can see over here, when you click on the debug, which is where all the output is generated, it's generated these LD files. And in order for us to build the executable for that particular target, we need to link this XD files, and it's not given to us, it's generated. And if you don't generate this, you won't be able to compile. So what does this file do? So the first thing we can see, it tells you over here that this is generated by using the create link free master, and it basically is telling you that we need to install this particular object files in order for us to compile the executable. It requires the CR no host, CRC, CR EABI helpers, and GCC, and it'll tell you, and then based on where exactly I've installed the your McuXpresso ID, in this particular case McuXpresso, whatever your manufacturer's ID, from there you can navigate and see where it's generated, and I'll show you exactly what it does. But why do we need to, why is there an extra step over here? And the reason why we have this extra step, and no matter what the chip is or who the manufacturer is because you need to compile your code based on a very specific target. That's number one. But two, that target might have, a different memory layout, would have different pin configurations. In this particular case, memory layout. And where do you want your code and how you want your code to be compiled to? Where do you want to start your execution? Where's your heap going to start? Where is, how your memory flows. And that's really the instructions that these things, that this particular file is doing. And it's telling, this is where the top RAM starts. This, the flash starts at this particular address. Your top flash is giving you where exactly in the address you can insert the code and which part of the memory address is assigned for what features and what functions. This is very important. You can't really come up with this stuff. This has to be provided by the manufacturer. That's why. And this is generated because they'll probably have a script that where you say if you're compiling for this particular chip, they'll have a template and then they'll fill in the addresses based on that. So that's why you need to do this, and you need to basically compile it for the first time, get this code, and then link it copy this LD file which is generated, because this will be common for any project now on. You can copy this file and then bring this into your link directory, into your custom build directory. And the same thing over here, it has this peripheral blinky underscore debug.ld. And it's basically telling you how it's aligned, where does the DRAM start, where does the RAM start, and I've not really gone in too much into the details as to what this code is doing. It's generated code, but in a nutshell, it's basically aligning all the memory and addresses and making sure, you know, it's giving instructions of how the build process is supposed to work. That's really it. All right. So how do I know how to get this file from and where it is? So when I download my McuXpresso IDE, it tells me that I need to go to the IDE tools, ARM, lib, thumb, VM, non-FP file. And how do I know about that? I can go to the map file over here. And when I click the map file, it's telling me where everything is linked and where's the path for all of this. So if I want to search for, okay, I need to get all these object files, I can search for where exactly it is fetching these object files, and I go to that path and then I copy it into the repository that I want. So that's how I'd go about doing it. So I basically copied all the libraries that are very specific, that this manufacturer expects me to link to for this particular target. I take those targets and I link it with my custom directory. So now when I go to my custom directory over here, I have my file over here. I basically, in my previous video, I basically went over here. I created a small script. I'm not using make for right now. I created a small little script that does that GCC, creates all the pre-processing directives that it needs to be compiled for. And then, you know, it basically is able to create the object file for the core. So when I click, you know, /script, it'll compile the code. And it's just giving you some warnings, which I think is fine for now. I don't need to go too much into figuring out, you know, whether it's going to cause any problems, but that's fine. So once you create the object file, then you can do the AR and basically it'll take all these ARs and archive them into one shared object, and then you can create the liblpc chip 1756.6x. Similarly, we need to do this for the other folder, which is the board support packages, which we did last time as well, where we go over here and then I created a small little script which does the same thing literally, but this time it's you know, compiling for this particular folder. I put in all the directives, the directives that needs to be linked for this particular processor, for this particular chip. Where is the library? Where is the include? So this is very straightforward till here. Like you can directly do this without linking those files because we don't need to link the LD files right now because you're just creating an object file. And once we do the script, it'll automatically create and then it'll compile to these .o files, and then we archive them into one object file. The tricky part now comes when we have to build it make it into an executable. So an object file is not an executable. It just has all the function definitions, and it's got the information of how to process particular functions. It doesn't give you, it's not an executable where it can just run. And that's what so when we go to say peripheral blinky, in this particular case, now we need to create an executable because we want to download this into the actual microprocessor or the microcontroller and make the LED blink. So it's going to be an executable, but this executable is going to have files that we just built recently. Is going to link with this particular object file and this particular object file in order for it to function. So this is where it gets tricky. So when I go to my script, and this is going to be a little bit it's got more information than the previous scripts, is because the first part is I'm basically saying compile all the C files into object file. Nothing wrong with that. When you're compiling a C file to an object file, you don't need to have too many instructions. When you're compiling from an object file to an executable, that's where all the linking needs to happen. Now you're telling, okay, this is an executable. Where are all, in order for this to work, I need to have all the information to make this into an executable. So what I've done over here, the second script we can ignore. But what I'm to say that this is just look at the third line over here. So what are we doing over here? So no standard lib is allowing you to, I'm not too sure exactly what the definition is, at least I can't recollect immediately. I'll let you know later, or maybe I'll have a video on that. But this is also when I compile on the McuXpresso IDE, I'm also taking all that information that I have not touched the build, but all that information is actually there during the build process, and I'm just taking that information and I'm pasting it into my small little script over here. And what I'm telling you over here right now is my library is now going to be in this particular folder. Create the map, create the linker, create the expressions, and then here, this is the important part. Please link with this peripheral blinky debug.ld. And I'm getting this file which was generated by the McuXpresso. All right, so this was expressed over here, and I just copy that file for me to build this. This is important because this has all the information of how the address mapping is going to be done. Create the objective, create the output. This is an output, and create the executable called peripheral blinky. Take all the object files and work with all the object files. That's basically what I'm telling over here. Compile all the object files, and this is the library. So you're going to link to the LPCXpresso that we just built. You're going to link to the LPC chip. And remember, we were talking about all those other libraries that we need over here that this LD file has. That is very specific, or it's the McuXpresso. When you download all those tool chains that it wants you to link to, I have that over here. So I'm basically giving them the path that you want to look for all the other libraries in this particular path. So it's going to look for in this path, and it's going to look for in this path. And from there, it'll pick up the libraries that we want, which is based on the LD file. And now when I do a small little /script, it'll compile all those object files into the target. And now what we have is a peripheral blinky.axf. And if I do an ls/alrt, we know it's not an empty file. It's alrt. We know it's not an empty file because even if I do a make clean, say remove this, and I remove this lx file, and now I do and I just run the script, right? So and then we'll see as you mentioned over here, I've copied these LD files into this root directory, and now when I do an ls/alrt, you can see it's compiled. This is the file size, and this is an actual executable. This is now a directory, a functioning system, or a directory where I can now start to add things onto it, layer by layer by layer, making it more compatible with the code that I want, with the targets that I want. And this would work for the same way if I'm doing a Nordic semi, if I'm working with our Atmel, and that's really it. All right, so now let us recap. The first thing you want to do is download the ARM GCC toolchain and add it to your path, which is basically making sure that when I say add it to your path, when you're using a bash script or whatever your console of choice is, make sure that when you type in the ARM GCC toolchain, you are able to access it without typing the full path. 2, organize your folder structure, as we mentioned and we spoke about it earlier in this video. 3, download the manufacturer's IDE BSP packages and then compile to get the generated LD files. These are the linker files that are necessary in order for you to do all the, to generate the executable in your custom directory. Then download the BSP package, the LD files to your custom directory. So now you take those BSP packages and move them to your custom directory. And last but not least, happy compiling. It's there's a little bit of effort that needs to be done in order to make this work, but I've already explained in the beginning of the video why this is important. And this concludes the series. Thank you so much for watching. Please if you find this informative and educational, do subscribe, because there's going to be a lot of this type of work that I generally like doing, which is very ground level, low level. It's not, like how do you, press a button and make, Blinky work. I like to really get into the details of what the code is doing, why the code is working that way. Am I as low to the hardware and working through those abstractions, and I am understanding those abstractions. I mean, that's what it really takes to build a product that people want. You can't fake this stuff. I mean, you can make something working as a prototype, but if you want to make a very reliable, robust product, there's that level of understanding these abstractions that very few people might want to take the time to learn, but it's important in order for us to make a good product so that we know what we're building. And if there's something wrong, I know exactly what to look for. I'll have some form of knowledge that very few people might have, or you might have, because you're going through the steps. So, you know, that's what this video series is all about. So please subscribe. I think it's very helpful once you really, you know, go through and do this exercise and really make sense out of it, and how, you know, you kind of feel really powerful about it. Thank you so much. And until next time, take care.